now we continue our day session, and our first speaker is Meirav Amram.
Hi, everyone. First of all, I would like to thank the organizers very much for this wonderful platform to share with you guys some good ideas. It is a wonderful workshop and I enjoy it very much, so thank you. One word, please. I saw in the morning the shirt of Sergey. And on the shirt of Sergey, it's written "Sweet Tears." So I wish all of you, I hope it will come soon, and I wish all of you very sweet tears. This is the first thing. The second thing is that I would like to tell you very briefly about my research interest. I am an algebraic geometer, and I work mostly in classification of algebraic surfaces. And I will focus on this today, but one sentence about the curves. I also classify planar curves, and I work mostly with the line arrangements and conic line arrangements. So now about my talk, I will speak, as you see, about the algorithm of the degenerations and the fundamental group. They are a very good tool to understand algebraic surfaces and to classify them in the moduli space. I give already my email in the beginning of the talk because maybe some of you will be interested in some information or papers, so you can have this email right away. So I will start now. We know that classification of, can you hear me and see the screen is okay? Everything is okay?
Yes, yes. Yes.
Okay, okay, thank you. So let's speak about classification. So if I say the word classification, for me, it means that I classify algebraic surfaces or curves. Curves can be branch curves, as I will explain to you today, or they can be just planar curves without any connection to a surface. Just very briefly about classification of curves. Maybe one sentence, and then I will focus all my talk about surfaces. So, classification of curves. So, actually, we find Zariski pairs. So, what does it mean? It means that if I take two curves, they have the same combinatorics. But they have different fundamental groups. When I say a fundamental group, FG along the top, I mean fundamental group. Please just remember this. And fundamental group for curves, it means the fundamental groups of the complements of the curves in CP square, for example, let's say. A very good references for this are the papers of Tokunaga, Banai, and Chiran. And here I stop and I speak now about classification of surfaces till the end of the talk. So classification of curves. So let us take X an algebraic surface. We take also a generic projection F from X onto CP square, and we get the branch curve S of X. So these are all the notations that I will use also along with the talk. I take it in CP square. Now, a very good invariant of classification is the group G. I will denote it right away. This is G. The fundamental group of the complement of S in CP square. So please also remember this notation, the fundamental group of the complement of the branch curve. I would like to remark to you, that actually G can be very complicated. So we will try to see later on what we can do with this, but now some example. Long time ago, I tried to deal with this surface, X equals to T times T, where T is a complex torus. I found out that the group G is generated by, you will see right away, by 54 generators. I denote them by gamma I. And it had more than 2,000 relations. So that was terrible at that time. And I found a nice way to recover from this by taking the fundamental group of the Galois cover of X. So the fundamental group of Galois cover of X. And you see that I denote it as X gal. Okay, this is the Galois cover of X gal. So maybe it was better to deal with this group rather than G itself. So now a question. What is so special in these groups? For example, in G or in pi 1 of X gal. What is so special in them? So the answer is the following, and therefore we are motivated to work with them. Surfaces that are in the same connected component, of course, in the moduli space. They have the same G. And it holds also for pi 1 of X gal, which is very nice thing. And now a fact which is well known to many mathematicians, and what was proved by many of them, is that if we take the quotient of G by the normal subgroup generated by the squares of the generators, and we project it onto Sn, the symmetric group, then at some conditions, we can define the kernel of this map, let's say phi, as the fundamental group of the Galois cover. I don't have time to enter to this because I want to focus in the fundamental group, itself. So I skip the proofs of such things because I have much to tell here. But this is a thing that we are going to use later on. And now, a very brief definition for the Galois cover. So if X is algebraic surface, F is again the generic projection of X onto CP square, and the degree of F is n, then we can define the Galois cover as follows. X gal is actually a fiber product of X n times. Let me write here n times. We eliminate the diagonal and take the closure. So good references for this, for all this covering matter and the Galois groups, you can find also in Chovansky. A remark to you that also this group might be very complicated, is not easy to calculate. Believe me, we had so many hard examples, and sometimes it is only possible. I say it's only possible because maybe someone can find a better way to do this, whether the group is trivial or not. I will give an example later on for this, for such a case. Now, I would like to present to you the following algorithm. Algorithm of degeneration. So, first of all, I will draw a picture of a diagram, and then I will explain what we are going to do with this. So we have X, an algebraic surface, this we know. We know that we have a generic projection F onto CP square, and we know that we have the branch curve S. Sometimes it is very hard to deal with the S, okay, because the picture is also very hard, very complicated. It's hard to draw a picture of it. So what we are going to do is we walk in a longer way, but maybe in a safer way to produce S, or maybe not S, maybe the group G directly. And I would like to show you this. So we take here the generation process, and we get here a degenerated object, which I denote by X hat. It is also in CP to the N. Here we have also something like a generic projection. And here I will get S hat, which is in CP square. It is the branch curve of X hat. After I get S hat, we can do a reverse process, which is called regeneration, and we can try and recover S and find directly the group, the presentation of G actually. So now, instead of doing this directly, this piece in the diagram, we are going to do all this way and return to S. But you will see it's very nice work, and it can save a lot of pain later on. So what is this? What is this now? I will give you some nice examples of a degeneration, because I am very interested in the geometry of such thing. So the first example of this can be the surface CP1 times CP1. It means that I take the first CP1, this is a projective line, and I take the second CP1, and I close this square, and I take the diagonal. Of course, there are proofs for everything, but I am short in time. But I will tell you only that we have two triangles here, and we can say that each triangle represents a CP square, some plane. So it means that in this case, X hat is a union of two CP squares. So this is the easiest case. Now, if I take the second example, I take the same surface, but this time with some different embedding. Let's say here I write 3 and 1. So I will take the first CP1 3 times, and the second CP1 I will take once, and I will close again this triangle, this rectangle, and take these 3 pieces with diagonals inside. So here, for example, I will get X hat as a union of 6 CP squares. Another nice example, which is connected to the terrible group G that I showed you before. Remember, with 54 generators and more than 2,000 relations. So why was this group so terrible? It's because the surface looked like this. It's T times T. I recall that it's a complex torus. And we know that the torus can be degenerated to a triangle. So we can take the first torus, and this is the second torus. I close this square. I divide this into the column and the rows for each one of the toruses. And I take these diagonals. And as you see here, X is a union of 18 planes. X hat, I mean X hat, 18 planes. And what is interesting in this is that if we numerate the vertices here, this is the first torus, so it's 1, 2, 3, and because of the identification, it will be 1. If I continue to numerate, it will be 4, 5, 6, and then again 4. And here it will be 7, 8, 9, and again 7. And because of the big identification, we have again 1, 2, 3, and 1. So you can see these singularities in the middle that are, for example, intersection of 6 lines. So you can imagine that when I regenerate them, what I get from all these types of singularities. Also here, for example, yes, this one. Oh, what happened? I'm sorry. You can see what happened with all these identifications. So this is another very, very challenging example. And the last one that I want to show you are the Herzograph surfaces. So if I take X and I denote it by HNIJ, this is for me Herzograph surface, this is how I denote it. And Herzograph surfaces degenerate mostly to some kinds of trapezoids. So let's say that if I draw a picture of a trapezoid right now, and I take these two triangles on the side, so when I say two pieces here, this is I. And if I say this one piece here, it means J. So in this case, X hat is actually H, a 2,1, and this N means the number of the triangles on the sides. So it means 2. And actually, here I close these nice examples, and I want to continue to the other stuff that I have for you. Before this, some very good references for all this subject of degeneration are the papers of Chiliberto, and also Chiliberto and Miranda and their research group. Now, I would like to recall the diagram, the above diagram, and let me please copy it in order to save some time. So I copy this diagram. Let me put it here. And we remember that we have a surface X, we have the branch curve S, but right now we degenerated our X into X hat, which is a union of planes. But now we want to see what is this? What is the branch curve S hat of X hat? So this is our next question. What is S hat? So let me take again the above example because it's very nice and very easy to explain on it. The one with the 3-on-1. I will draw it again and we will work on it. So I remind you that this is X hat equals to 6 to union of 6 planes. And I enumerate here the edges, the intersecting edges is 1, 2, 3, 4, and 5. And what is actually S hat? S hat is the union of these images of the above edges. So actually, I can also enumerate the lines here. These are the images of the edges above, and we see that S hat is a union of 5 lines. So it means that S hat is a line arrangement. And this is something very interesting by itself, also to investigate line arrangements. It's very interesting. I would like to remark that regenerating S hat to get S is a very nice process, but we skip drawing the picture of S. It's very hard to draw the picture of S, but it is enough for us to understand the structure of S. And this gives me already the fundamental group G. So what we do is that we compute directly G and pi 1 of X gal. So just to note that here, look in this picture, please. Here you can see some points, some singularities in the line arrangement. These ones are very easy to regenerate, but in the last few years, I found some nice regenerations to even higher multiplicity singularities in some works, but I don't have to speak about this in this talk, maybe in another one in the future. Because I want to keep the rest of the talk speaking about the fundamental groups itself. The important thing that I can get from all this process is that we pay attention that after regenerating and getting S, so the curve S is cuspidal with nodes and branch points. This is the most important for us to know when we regenerate. So we are going to have branch points. When I say branch point, it means this point in a conic. So this is a branch point. It is locally defined by y squared equals x. This is a node. This we also allow to have a node, which is defined locally by y squared equals x squared, and by a cusp, which is locally defined by y squared equals x cubed. Then, when we know that we have only these types of singularities in S, we can turn finally to Van Kampen Theorem. So Van Kampen Theorem gives us the presentation of G, I mean this G, Cp squared minus S. It gives us a presentation by means of generators and relations, of course. So let's see what we conclude from Van Kampen Theorem in our case. So if we have a branch point, then the relation that we get from this is some equality between two generators, gamma I and gamma I plus 1. What do I mean by this? If I take the x-axis here and the conic, this is the branch point, and here I take a good point, and I take two generators of the fundamental group G, say gamma I and gamma I plus 1. We can substitute some loop inside the equation, and we can get it. And of course, I will show a proof for one of them later on. I just want to finish the list of the relations. So this is what happens. These are the loops of G. If we have a node, we will get a commutation between the two generators, which I denote by this thing. It means that gamma I plus 1 equals to gamma I plus 1, gamma I. And if we have a cusp, then I get some relation that looks like this. Gamma I plus 1, gamma I equals to gamma I plus 1, gamma I plus 1. Now I would like to show you by the Van Kampen Theorem how we get, let's say, the relation for a node. So very short, a nice proof. So let's say assume that I have a node here. This is the x-axis. This is the singularity, and this is the projection onto the x-axis. So I take again a good point M, which is here, let's say, and I take the two loops, gamma 1 and gamma 2, that encircle these two arms that meet at the point of the node. And we know that the equation, the local equation for this is y squared equals x squared. Now I take a small loop of M around x, and I denote it by e to the 2 pi I t. Now, if I take this one and I substitute here, you can see that we can get the following thing. So this is gamma 1, and this is gamma 2, and this is the good point M. So what we get actually is a full twist, a counterclockwise full twist of gamma 1 and gamma 2 around each other. So we can get something like this. This is the new gamma 1 hat, let's say. And this is gamma 2 hat. And Van Kampen Theorem, there are a few versions, of course, for this, but Van Kampen Theorem, the original one, says that if we have this type of new loops, they are supposed to be equal to the original ones. So it means that if I walk along this loop in a counterclockwise movement, then I circle the point and then I return back, then I can get the following relation. Gamma 2, gamma 1, gamma 2 minus 1 equals to the original gamma 1. And for the second loop, if we walk on it, we will get gamma 2, gamma 1, gamma 2, gamma 1 minus 1, gamma 2 minus 1 is gamma 2. And you can see that we get the commutation between gamma 1 and gamma 2. And it's a very nice exercise to do it also for the other cases. Now, I would like to recall that from above, that when we took this quotient and we projected it onto Sn under some conditions, we could get the kernel, which is the fundamental group of the Galois cover, because now it's the time to deal with this group after we get the group G by the Van Kampen theorem. So how is phi defined? We need to understand this map. So of course, if I have another, again, this picture, this nice picture that I love to work on it, and I enumerate the lines, the edges, 1, 2, 3, 4, and 5, I can say that each edge corresponds to one generator in G. So this means that we will have gamma 1, gamma 2, gamma 3, gamma 4, and gamma 5. Now I would like to number the planes as 1, 2, 3, 4, 5, and 6. And what happens is that when we have the phi maps each one of the generator to a transposition in Sn. So it means that here gamma 1 is mapped to 1, 2. This is mapped to 2, 3, and so on. I will just complete the transpositions. And of course, it is nice to work with transposition rather than maybe to work with gammas and thousands of such heavy and complicated relations. I would like to give you a few results from all this because my time is very short, so I just want to give you some nice things. And of course, if you are interested, you can contact me in the email, and I will give you all the right information about this. So there is a joint work with Gong and Mo. By the way, Mo gave a talk yesterday. So we found out that the fundamental group of the Galois cover is trivial for all K. What does it mean? For all the surfaces that degenerate to Zapatic RK singularities. This is RK. Also good reference for these ones are the paper of Chiliberto because he computes all this. This is the first result. There is another nice result, a joint work with the Gong, Sinichkin, Tan, Xiu, and Yoshpe. We took all the 29 possible cases of the generations of degree 6. I speak about the planar ones, only about the planar ones. And we found out that 20 cases from this 29 generations have a trivial fundamental group of the Galois cover. 8 cases are non-trivial. And there is another, you see 29, here we have 28, and one was open question. I think that maybe it was solved. And the last thing is that there is a new study about a non-planar degenerations, because till now, of course, we dealt with some non-planar degenerations, but there were only sporadic cases. But it's nice to see the systematic study about this. So this is concerning writing to you. And in 1 minute, I want to show you, I'm almost in the end of my talk. And for the end, I want to show you something very nice. Please see this. This is a computer algorithm for the group G that I developed with Sinichkin from Tel Aviv University. I just want to note that this computer algorithm does not simplify the group G, but it simplifies all the way long to compute the group G. For example, if I give a planar curve, so it can be a planar curve with no connection to a surface, or it can be a branch curve. I just point on all the singularities in this planar curve. So the first output of this nice algorithm is to get a monodromy table that I also skipped in the work in this talk because of the short time. But you can see 15 singularities according to the 15. According to these 15 singularities, you can see here 15 lines. The second output that this algorithm can give me is for each one of the singularities, I can get a braid and the induced relation in G. So this is, for example, for the first singularity, and then also for the second singularity, we have a braid and the induced relation. Also for the third singularity, you can see all the process to get the braid with the picture and the induced relation, and so on. The computer algorithm repeats itself 15 times for all these singularities, and the last output is actually all the relations together in G. And of course, with this initial presentation, you can do what you want. You can simplify it by hand, you can put it in Magma, or you can consider some nice quotients of the group, and you can join us to this classification of surfaces and curves. At this point, I finish my talk, and I would like to thank all of you for all the participants, and to you, amazing organizers, for this wonderful conference. Thank you very much.
Thank you for your talk. Thanks. Do you have any questions, please?
May I ask a question?
Yes, please.
Yes, it's very, very interesting. Thank you very much. The question is, the first one, is it possible by your methods to compute or distinguish higher homotopy groups of this complement?
Oh, so this is actually a future plan. Yes, this is actually a future plan. We can take, yes, we can do it. For example, by some abelianization, or yes, this is we had some discussions about this.
Because it looks like if you get that you get some surfaces which are simply connected. So this means that you have spheres, yes, two-dimensional spheres, just something like partition in two-dimensional spheres or something like this, or not. This complement, the complement to this surface, to this S, splits, is fibers by two-dimensional spheres or not? Or maybe I did not get
to which dimension? Sorry, I cannot hear you.
No, one. Just sorry, maybe I make microphone.
Oh,
so, now it is better.
Yes.
Oh, sorry, my microphone.
Yes.
Excuse me. So,
yes,
if you consider this complement, as I understand, it is not fiber, but it is a union of two-dimensional spheres, or curves with fundamental group 0, or not, or maybe I did not get this correct.
No, it's not. No, it's not always the case. It's not always the case. Only the G is not always like this. The fundamental group of the Galois cover, mostly because you add more conditions because of this special quotient, then it might be trivial sometimes, not in all the cases, but yes, about these fibers from S back to X, it depends on the degree of the generic projection. You can see it with you can see it when I had this diagram with the X hat. Then it's according to there are some computations there, but it's you need to see how many triangles you have, and to take some regeneration limitations and so on. But also there you get some conditions on S, on the degree and everything, but it's not always. It's not always.
I understand. I understand. Okay. Yeah. Okay. Thank you very much. Thank you very much. Very interesting. Thank you.
Thank you.
Any questions, please?
I have a question.
Yes.
So the surfaces you consider, they are open, right? They are with singularities, correct? So these groups, these presentations and relations are for singularities, right?
Yes.
What happens if you compactify the singularities? Can you kill some of the relations? Just like with Riemann surfaces, right? You have the open curve, then you put back the points, and then your relation collapse to something simpler.
Yes, because you mean the projective relation that we need to add when we move from the affine to the projective case.
Yes, compactification. For me, you think about this projective.
Yes.
I just think about this in a primitive way of putting back points or
yes,
planes.
Yes, so actually, instead of putting all these points, we use the projective relation, which is the product of all the generators. It's the identity. Yes, it's like to take a big loop around the
That's
circle.
It? Only one relation is added?
Yes, in S, in the fundamental group G, yes.
No, for the one-dimensional case, I agree with you, but it's really surprising to me that for these surfaces, you only have one relations when you compactify. So it's really surprising.
When actually it is hard to see the compactification of all the surface. We take the affine pictures. Sometimes it's yes, it is a hard question. It is a hard question to
because probably it will happen what will happen in the Riemann surface theory, right? I mean,
yes.
You will have a collapse of relations, and you will have a much simpler groups.
Yes. So actually, we focus on groups of the planes, of the curves. About the surface, I need to think about this.
Okay.
Do you mean you speak about finding the group for the surface itself?
Yes, for the compactification, right?
Yes. So,
right, because you use Moishezon, the techniques were developed by Boris Moishezon and Mina Teicher to do this, right? But I've never seen them doing the compactification. Maybe it's too hard, because if Moishezon couldn't do it, then it's pretty hard, right? But maybe it's something that you guys can think about, you know.
Yes, it's a good idea. You give
because
me
in curves it's pretty straightforward.
Yes.
Another thing that I wanted to ask you, let's say you have an open curve given as a ramified cover of the sphere, right?
Yes.
So you can get the fundamental group through Van Kampen, but can you also define the intersection form in some sort of a functorial way?
Again, can you please repeat this question?
Right, so you have the curves that create the fundamental curve, the fundamental group of the curve, right? Can you see the intersection form, right? When the curves are intersected, can you see kind of if it's what kind of intersection you have there, right?
Oh, yes. I skipped it in the talk because I didn't have time, but of course, you have all this intersection between the planes.
Exactly.
It's not easy to do them, but I reached already to singularities up to multiplicity 10.
Okay, very good.
It's very complicated to continue more than this, but we think about all these directions.
Okay, beautiful. Thank you.
Thank you very much.